We're now ready to start chapter 4. In chapters 4 and 5, we're going to be dealing with the same kinds of functions. We're going to be dealing with functions of several independent variables. Now, this could be a function z equal to a function of x and y, or it could be a function w of x, y, and z. It could be a function, w of x, y, and t, or even w of x, y, z, and t. We could have many, many independent variables. This brings us into 3 dimensions and 4 dimensions and possibly even 5 dimensions. When we study these functions are real valued functions. They're scalar functions. They're not vector valued functions as we were looking at in the previous section or the previous chapter. One thing that is a good idea is to make sure that you've reviewed the section 2.6 on quadric surfaces. Quadric surfaces and cylinders are good examples of functions of multiple variables. Z depends on x and y. So we have 2 independent variables, x and y, and z, the dependent variable, depends upon them. In chapter 4, we'll be looking at differentiation with these functions of multiple variables. And in chapter 5, we'll look at integration of functions of multiple variables. So we're going to kind of switch gears here from our vector valued functions to focus instead on scalar valued functions. Now, when we're doing this, the first thing that we want to do is we want to learn to identify the domain and the range of these multivariable functions and learn how to graph them. We're also going to look at ways to relate the graphs of functions in 3 dimensions to graphs of more familiar functions in 2 dimensions. So we'll be taking images of these 3-dimensional shapes and projecting them into the plane to see what they look like from different directions. Now, the definition of a function of 2 variables is very similar to the definition of a function of a single variable. Now, when we talk about a function of a single variable, what we're talking about, of course, is a function such as f of x equal to y. So this could simply be something like y equals x squared plus 3. In this case, f is the function of a single independent variable, which is x. Y is the dependent variable which depends upon it. We put in the x value from the domain, and we receive the y value, which is in the range. When we're talking about functions of 2 variables, then we will have a function, let's say f of x and y equal to z. Now, ours may not always be x, y, and z, but this is a good example and a very common occurrence. In this case, x and y are both independent variables. And what happens is the domain, as you can see on the image on the left, the domain consists of some subset of the 2-dimensional space, the xy plane. In other words, all of R2. And we take an ordered pair, an x value and a y value, from the domain, and we map it by means of this red arrow to a single real value in the range, which is z, the dependent variable. It's very, very similar if we have a function of 3 independent variables. If we have a function of 3 independent variables, we actually end up in 4-dimensional space. Now, it's very difficult, it's impossible to draw 4-dimensional space, that we can draw images of 4-dimensional space called level surfaces, which we'll see later today. In this case, the domain is not the 2-dimensional space R2, as in a function of 2 variables, which exists in 3-dimensional space. But instead, if we have a function of 3 independent variables, the domain itself is 3-dimensional space, R3. And we're mapping R3 onto some single real value, say w, which is in the range. And this puts us into 4-dimensional space because we have 3 independent variables, say x, y, and z, and one dependent variable, say W. Our learning objectives for this particular section are to recognize a function of two variables and identify the domain and the range. Now, the domain is going to start the way it has always started in college algebra and calculus. We start with the default of all reals, except anything that would make it undefined or have a negative under an even radical, things like that. Zero in the denominator, can't have a non-positive number inside a natural log. Those kinds of things will restrict our domain. The range would be the values that actually come out of the multivariable function. We're going to also sketch graphs of these functions of two variables. And again, I expect my students to do most of their graphing in CalcPlot 3D or some other 3D grapher. Then we're going to sketch several what are called traces or level curves of a function of two variables. Briefly defined, a level curve is, let's say that I give you a function of two variables, but I tell you I only want you to consider when the z value, the dependent variable, is 5. So find all the x and y values that give you a z value of 5. That would be a level curve for that three-dimensional surface, only looking at a particular value for the dependent variable. Traces do the same thing, but in the other planes. Then we want to recognize a function of three or more variables and identify if it's a function of three variables, its level surface. And again, a level surface is a very similar idea. Let's say that we come back to this situation on the right, where we're taking an ordered triple from three-dimensional space, an x, y, z, and putting it inside of some function and getting out a real value w. If we're doing that, then how can we visualize this in four-dimensional space? We can't. But I could say, let w be 11. What does it look like when w is 11? That would give me a function in 3 dimensions, and I can graph that, and it would look like a surface. So what we often do, if x, y, and z represent position and t represents time, is we'll show snapshots of the level surfaces as time progresses. Let me share my screen with you, and we'll get started in section 4.1, where we're going to talk about these functions of multiple variables. We've talked briefly about what a function of several variables is. Basically, we have more than one independent variable. So it's no longer just a function of x or t as it was in Calculus 1 and Calculus 2, but now in multivariable calculus, we have functions of more than one independent variable. We can have multiple dimensions. So when we define this, let's see how it affects the definition of the limit, the derivative, and the integral. We're going to start with the formal definition of a function of n variables, where n, the letter n, is representing an arbitrary number. Now, it does have to be a finite number, but we could have 42 independent variables. In fact, linear algebra deals with just such functions on a regular basis. In this case, we would say that z, which is equal to our function f, is x sub 1 plus x sub 2 plus x, or not plus, but comma, x sub 1, x sub 2, x sub 3, x sub 4, x sub 5, all the way up to whatever n is, x sub that number. So if we have 42 independent variables, it would go up to x sub 42. And this would describe a 42 tuple, if you will, an extension of ordered pairs and ordered triples from a subset D of R to the n. If it had 42, it would be R to the 42. Now, in our case, we're mostly going to deal with subsets of R2 and R3. So we will be looking at functions of two variables, which exist in three-dimensional space, and functions of three independent variables, which exist in four-dimensional space. This set D is called the domain of the function. It could be all of R2 or all of R3. It's the ordered pairs and ordered triples from R2 and R3 respectively that work inside the definition of that particular function. In other words, the ones that don't give us negatives under even radicals, don't give us anything but positives inside the argument to natural log, and don't give us zeros in the denominator. If we have that, then this n-tuple coming out of the domain gets mapped to a single real number. And this real number is the output of that function. It's called the range. In such a way that this value, and here we've used z, but we could have used something arbitrary. W is often used arbitrarily. W equal to this function of x sub 1, x sub 2, all the way up to x sub n. Let's take a look again at the pictures here so that we can compare and see what we've got. This blob that you see drawn on the left is a subset of R2. So the domain is a subset of R2. Now it could be all of R2. And when I say R2, I'm talking about the XY plane. Right? So yes, the normal graph that you're used to seeing with y going up and x, positive x going off to the right. We take these ordered pairs and map them to a particular z value. And this will produce an ordered triple. And we'll graph the ordered triple in order to graph the surface. So we'll get an xy from the domain mapped to a z, which gives us an ordered triple x comma y comma z. When we look at a function of 3 variables, again, this blob on the left is no longer in the plane. What's coming out of this domain are ordered triples. So this domain is a subset of R3. And that means that it's a subset of 3-dimensional space. What we normally think of when we think of z being positive going up, x coming out of the screen, and y going to the right. That entire space that, well, we live in. That is our domain. We take the ordered triple and we map it to something else. So this could be something like, oh, I don't know, x, y, z could be position of an object, and w could be velocity of the object at that point, right? Or something like that, temperature of the object at that point. So it's a relationship between the ordered triple and the output, which is in the range. When we're finding the domain and range, it's easier to do by simply looking at an example. So I want to go ahead and start with example 1 that you see here. We have a function, and we do use function notation for these. And the function notation, if this is a function of 2 independent variables, has x comma y inside the parentheses. Again, just like in regular function notation, there's no x, y on the left. This represents the dependent variable. So when we think about this, this is really representing the equation z equals the square root of 36 minus 9 multiplied by x squared minus 9 multiplied by y to the second power. Now, when we think about this, we have to think about the domain and the range. If I think about the range, I think about what kind of z values could come out of this. Well, first off, it's a square root. So, and there's no sign written out front, so I know it's not negative. So could I get 0 out? Yes, I probably could get 0 out, but I can't get anything negative out. So my range is going to go from 0 out to infinity. What is my domain? What values can I put in here? Remember, the domain is now a subset of 2-dimensional space. It's a subset of the xy plane, where this is x and this is y. So our domains are not going to be intervals exactly in the same sense that they were in calculus 1 and 2. In this case, I know that because this is a square root, that the radicand, the part under the radical, must come out to be strictly non-negative. And that tells me how to get started. I need 36 minus 9x squared minus 9y squared to be greater than or equal to 0. Now I can go ahead and move the variable terms to the opposite side, which gives me 36 is greater than equal to 9x squared plus 9y squared. And I can notice that there is a common factor of 9 on both sides of this inequality, and I can divide everything by 9. When I'm dividing by a positive value, I don't reverse the inequality symbol. If I multiply or divide by a negative, I do reverse the direction of it. And this gives me 4 is greater than equal to x squared plus y squared. You could also rewrite this as 1 greater than equal to x squared over 4 plus y squared over 4. In this representation on the right, it looks more like the equation of a circle of radius 2, and it is. And the representation on the left, it looks more like an ellipse, where the length of the major axis and length of the minor axis are the same. In other words, it's a circle of radius 2. So whichever one makes the most sense to you, put it in that form. Now, in this case, what it's actually saying is that 4, which represents the radius squared, is saying that the radius squared is greater than or equal to that. So 4 has to be greater than or equal to x squared plus y squared. So what does that look like? Well, first off, if it's on the equation, if it's equal, it is a circle of radius 2. So the first thing I do is I graph a circle of radius 2. It can be equal. If it's equal, what I'll get under the radical will be 0. In that case, it's still defined. The output would be 0. The range value would be 0. So I use a solid line for the circle on the outside. The next thing is that the radius could be, must be, less than or equal to 2, which means that I can take x or y values that are inside the circle where the radius is less than 2, or I can take them on the circle where the radius is 2. Believe it or not, this blue circle right here, radius 2, centered at the origin, is the domain of this function. So how could we write the domain of this function in a way that sort of makes sense? So we can represent the domain with the letter D, and we want the set of all ordered triples x, y. Long vertical bar means such that x squared plus y squared is less than or equal to 4. So this is a way of representing all the ordered pairs that satisfy this equation. And that would include every ordered pair inside that blue circle and on the blue circle. Now the range values I can give as coming here. So what would the range be? Well, I know it could be 0 or higher. So does it go to infinity or does it stop? Well, in order to get this to come out, what's the largest possible value that I could get from the radicand, the part under the radical? Well, I'm subtracting 9x squared. X squared must be strictly positive, so minus 9x squared, well, it's always going to be negative or at most 0. The same applies to negative y squared. In other words, to maximize the number under the radical, I should let x and y both be 0. That makes the number the largest possible. The largest possible then would be 36, and the square root of 36 is 6, and it can certainly be 6. So my range is from close 0 to close 6. Let's now take a look at the next example. Well, before I do that, let's take a look at this out on Calcplot 3D. This is what that particular function looks like. It's the upper part of this. So when we're looking at this right here, you can see the upper part. It looks sort of like a, well, It's half of an ellipsoid or circular ellipsoid. All right. So now let's take a look at example 2. In example 2, we again have a function of two independent variables, x and y, but our function equation is the square root of x plus y. Now, again, we need to think about what could come out. Definitely, because it's a positive radical, the smallest value is 0, and it's going to go towards infinity, but I don't yet know how far. In the last example, it could only go to 6 and had to stop. In this case, again, we start by saying, well, the square root will only accept non-negative values. So I know when I'm looking for the domain that x plus y has to be greater than or equal to 0. And then I can solve for y, and this is going to give me a linear inequality, y greater than equal to negative x. If y equals negative x, that's the line of slope -1 passing through the origin that you see graphed in red here. Now, if y is greater than negative x, then that would be the region above. And again, when you're doing inequalities, you can always take a test point in a region to see if it works. So for example, I might take the ordered pair 0, 1 and see if that works in the inequality. Is 1 greater than or equal to -0? And the answer is yes, that's true. So that side is the correct side of the inequality, which means that in this case, I don't have a maximum value on my x and my y that can go way, way out, right? In other words, every value that is in this half of the entire xy plane is going to work inside my domain. So when I write down the domain for this one, again, what I can do is I can write down the equation giving the domain in terms of the ordered pairs. The domain is the set of all xy, long vertical bar, such that y is greater than equal to negative x, or you could have written x plus y greater than equal to 0. Either of these is fine. Now, what kinds of values would I get out? Do I have any upper end on my range? I've said the minimum value on the range is going to be 0 because it is a positive square root. But notice that the x and y, this green space doesn't stop with the right triangle shown here. It goes forever. It just stays above the red line, which extends in both directions forever. That means there's no limitation on x. X goes to the right forever and y goes up forever, which means that I have infinity plus infinity. So I definitely can go to infinity. So my range is closed 0 to infinity. And let's take a look at what this one looks like out here in our space. By the way, if you click on this one and you take the Z out of the picture by doing Alt-Z, you can see the domain. This is the domain of our first example, the circle of radius 2 and all the points inside of it. Let's look at our next one. This one has already taken all of the Z out, and you're again seeing the plane. Now, I had to play a little bit with the values of x, y, and z, the scale, in order to get a good picture of what the function looks like. So when you rotate off and you turn it around, what you're getting is sort of a curving, like a curving sheet of paper coming up like that. There is a curve to it, but it's rather slow because z is equal to the square root of x plus y. So it does increase towards infinity, but rather slowly. Let's take a look at example 3. Example 3 is similar to example 2, but not the same. In example 2, x plus y was combined under a single radical. Now we have the square root of x plus the square root of y, and they're separate radicals. This tells us that x has to be strictly non-negative and y has to be strictly non-negative. That gives us basically quadrant 1, the positive x-axis, the positive y-axis, and the origin. That gives us all the points that are here outlined in the red and the green space, with the green space continuing for all of quadrant 1. How are we going to write the domain for this one? Again, you can simply give it as a set of all ordered pairs xy, long vertical bar, such that, and then give the rule. X is greater than or equal to 0, y is greater than or equal to 0. You could also describe it in words, which would be positive x-axis, positive y-axis, the origin, and all the points in quadrant 1. What about the range? In this case, x increases without bound to the right, so the square root of x goes to infinity. Y increases without bound up, which means the square root of y increases to infinity. So again, we need to look at the minimum and the maximum. The maximum is going to infinity, since infinity plus infinity is still infinity. But the minimum value I can get out of a positive square root is 0. So my range is similar to the last one, 0 to infinity. I believe we have one more example to work. Let's first take a look at this one over here. So here is my space. You can see that, like the last one, it is curving. It's going up at a different rate, however, because the square roots are split apart. And again, if you want to kind of visualize the domain, take the Z out to look at the XY plane. Hold down Alt and hit Z, and you can see it's going out into quadrant 1, including the positive half of the X and Y axis and the origin. Let's now look at example 4, which is more complicated. In example 4, our function of two variables is the natural log of the quantity 9 minus x squared minus 9y squared. Now, what do we know about natural log? The argument to natural log must be strictly positive. It cannot be 0. The natural log of 0 is not defined. Recall that the natural log function kind of comes up and then arcs up at an angle, right? It does go to infinity, but very, very slowly. But as it approaches 0 from the right, it goes to negative infinity. It's not defined at 0. So in this case, when we're looking at this particular one, we'll take out the argument, again, starting the way we've been in the past with the radicals, and we'll say that this equation here has to be strictly positive. The best thing to do is to get the terms to be as, well, positive as you can. So what I'm going to do is I'm going to separate the 9, the constant term, from the y squared and x squared terms. The next thing I want to do, because I don't recognize the equation yet, is I want to go ahead and divide by 9. Now, it's not a totally common factor since the x squared term does not have it, but this will result in x squared divided by 9 plus y squared. Now, we can always write the y squared over 1, which puts it in fraction form to match the x squared divided by 9. This is the equation of an ellipse, which opens with the major axis parallel to x, in fact, on the x-axis, since the center is 0, 0, and it goes out 3 to the left and 3 to the right. So it has a major axis length of 6. It moves in the y direction up 1 and down 1, so the minor axis has a length of 2. So, but what we're saying is that it has to be less than that. So what we're actually going to do is we're going to graph the ellipse, but we're going to use a dashed line or a dotted line for the ellipse because it cannot be on the ellipse, but it can be inside of the ellipse where the relationship is smaller. So when we do that, you'll see that equation or that expression down here. You can see that the ellipse is graphed with a dashed line And the domain is the set of all points on the inside of it. So it's the set of all ordered pairs inside the ellipse, which has major axis 6, minor axis 2 centered at the origin. So we can write the domain as the set of all xy such that, and we can give the rule in whichever form we like, but the most clear would be to give it in the standard form for an ellipse. Now, what do we get out of this? What is the maximum possible? What is the minimum possible? We know that natural log has sort of this shape. So we know it goes from negative infinity to infinity slowly, but it does get there. So the question is, are we looking at a subset of that? Well, if we look at this, we know the argument has to be strictly positive. In order to make this a positive number, what could I do? Well, to make it a positive number, one thing I could imagine is what if the x and the y were both zeros? If they're both zeros, then I'm not subtracting from the 9 anymore. So that would give me an upper end for my range. The largest value that the range can be is 9. So in that case, my range is the natural log of 9 on the upper end. So I've got the upper end, and it can be that, so I use a square bracket. Now, what's the smallest it can be? Well, the x value and the y value can get small. They have to stay inside the ellipse, but they get smaller. And what happens? As long as this stays with the x and y value inside the ellipse, they will never overpower the 9, but they will drive the argument towards 0. And when natural log approaches 0, it goes to negative infinity. So the range is going to go from negative infinity up to a maximum value of the natural log of 9. Let's take a look at a picture of it, which you can see right here. And we'll go ahead and look at it out here on CalcPlot 3D. When we look at it on CalcPlot 3D, this one's kind of cattywampus. Let me take the box off, and then I can hit the home key, which for you may be hold down the function key and hit the left arrow key. To me, it looks kind of like a popsicle, like a fudgesicle or something like that. And what's with this green dot at the top? Well, the green dot at the top represents the maximum value of the function. When x is 0 and y is 0, the z value is the natural log of 9. So that represents our maximum value on this function. And I plotted it in green. Now, it goes down forever. You may ask, why isn't CalcPlot 3D going down forever? That has to do with what the Z clip is and how far I graphed it on my particular graph. If I zoom out, it will graph more and more and more, but it has no minimum. It goes down forever and ever and ever. If I were to take the Z out, let's take a look at what that looks like. And it's not drawing it super well because I'm only using a certain number of grid lines, but basically what you're getting there is an ellipse. Now let's go ahead, the ellipse that you see here. Let's go ahead and talk about some more terminology. When we graph a function of two variables, as you can see from the CalcPlot 3D examples, what we end up with is a surface in three-dimensional space. So it's a surface in three-dimensional space. A function z of x and y gives us a surface. Every point that's in the domain of the function lies entirely within the xy plane and maps to a unique z value, and that makes it a function. Let's take a look at what a level curve or a contour line is. If you've done any hiking, then you know what these are because you see them on all kinds of topographical maps. So this is a picture of Devil's Tower in Utah, and this is a topographical graph. I'm getting the wrong word, topographical graph of what it looks like to approach Devil's Tower. Now, when you look at the map, you can tell that there are these wavy lines that are coming around here. These are called contour lines. They are, in fact, level lines or level curves. Level curve is when we set a z value to a particular value. On a map, they correspond to a particular elevation. On most topographical maps, the lines are 40 feet apart. So to go from this line to this line means that I'm going up 40 feet in elevation. Now, the interesting thing about these contour lines or level curves is that if you walk along the level curve, you're hiking along a level line. So you're walking essentially on a flat surface. If you go across the lines towards higher elevation, then you're climbing up. If you go across the lines but towards lower elevation, you're going down. And we're going to learn that this has important applications to something called the gradient. What is the steepest way up or the steepest way down? Well, it would be at a right angle to the contour line at that particular point. Let's take a look at some more of these. Here's my home mountain, which is Green Mountain in Jefferson County. And you can see that there are various contour lines here. And again, you can tell where the peaks are because they sort of form a loop around that one point. And this is the top point of Green Mountain. When you come down one elevation, you're at whatever that is right there. Over here, you're at 6,600 feet. So the next line up would be 6,640, then 6,680, and 6,772, and so on. And so you can tell what the elevation is. Here's another mountain in Colorado. This is Thoradin Mountain. And one of the things that you can tell about these graphs is as the lines get closer together, what that indicates is that the elevation is changing more rapidly, which means it's steeper in that location. When the lines are further apart down here on the bottom right, then there's less elevation change, so the ground is flatter, all right? Walking along the same line means that you're walking on a flat surface at that elevation. Let's take a look at a topographical map of the New Orleans area. Now, New Orleans is a very low-lying area. It is flat, flat, flat. So this is, I can't remember, I think this is about 120 square miles or something. And essentially, you only see one contour line. In other words, there's only one change of 40 feet in elevation. It's all fairly flat, close to sea level. All right. The definition of a level curve of a function of two variables and a contour line are essentially the same thing. If you have a function of two variables, x, y, and you take some real valued constant c in the range of the function, then a level curve for that value of c is the set of all points for which the function equals c. So for example, I could set c to be 15. What are all of the ordered pairs that give me 15 for the z value? The graph of that produces a level curve or a contour line. So we choose a value for z, set it to be c, and then we plot the 2D curve. Contour lines or level curves are essentially 2D curves in the plane for that level or that value of c. Now, a level curve is always in the xy plane. It's always setting z to be a constant. If we want to set x to be a constant and allow y and z to vary, we don't call it a level curve, we call it a trace. And we'll look at those a little more closely in a moment. Let's talk about what a contour map is. When you plot level curves or contour lines on a single graph, it is called a contour map. And that's what our topographical maps are, like the maps I showed earlier. Let's look at the equation g of x. Oops, this should be g of x comma y. So I've got a typo there, so I'll need to go back and fix that one. G of x comma y equals the square root of 9 minus x squared minus y squared. G of x, y represents z. The domain is the set of all x, y that satisfy that equation. This would be all of the points that are on the circle x squared plus y squared equals 9, or inside that circle of radius 3. Let's suppose we choose different values for C, which is our Z value. Then the contour map would look like this. So if C equals 0, then we're graphing that circle of radius 3. If C equal to 1, then we're graphing the square root of 9 minus x squared minus y squared equal 1. If we have C equal 2, then we're graphing 2 equals the square root of 9 minus x squared minus y squared. So it's giving us a two-dimensional representation of what the surface looks like for one specific dependent variable value. Here's an image of the circular paraboloid with some of the level curves shown on the surface in yellow, right? Let's go ahead and look at example 5, where we're going to take another look at the example we did in number 4, which was our natural log of the quantity 9 minus x squared minus 9y squared. If we come over here, and this is that function, so I want to go to a normal view, so I'm going to hit the home key and get back to a normal view of it. This is the one I'm looking at. And if I have that there, how can I produce some level curves? I want to click on the contour map symbol, which looks like a series of sort of concentric circles, 4 of them on a graph. Let's go ahead and take a look at that now. So I'm going to click on this symbol right here, and it's going to open up a side menu. The first level curve is going to be the first value that it allows z to be. Default is set at -1. Then it has what it calls a step size. So it's going to do -1, then -0.8, then -0.6, -0.4. In other words, they're 0.2 apart in increasing order. Let's say that I go ahead and start at -1, but let's say that I want to make them 0.5 apart. The number of contours that it's going to graph is going to be 11. So it's going to start at -1, then graph -0.5, then 0, 0.5, 1, 1.5, 2, 2.5, until it's graphed 11 different contour lines. We can choose what color we want it to plot in by clicking on the contour color right here. Red may or may not show up well on this particular plot, so we might want to choose something like yellow or even white instead. Let's choose yellow. We're going to show the contours on the surface. Notice that it's giving me the list right here of exactly which 11 contour lines it's going to draw from -1 up to 4. It's not going to create the contour plot until you click on Create Plot. When you click on Create Plot, it's going to produce a 2D image. And unfortunately, they're not showing up very well because they're yellow. So let's change them to red and click on Create Plot again. And now I can see them starting to come out a little bit better. Notice that they get closer together towards the edge because that shape falls off and becomes extremely steep. So the closer the lines are together, the more rapidly the elevation is changing, the steeper it is. And this, of course, green dot is our maximum point, which is still plotting in the middle. Now, if you want to see where these contour lines are on the particular shape, move your cursor into the graphing region and just click one time. And when you do, you can see the curves right here. In this particular view, they'll probably show up better if we made them yellow. And I'm going to scroll in so that you can see them. And let me come back over here, click on contour plot. Again, choose yellow for the color, create the plot, then click here, and now you can see them. And we can scroll in a little bit so they show up better. One of those is a level curve or a contour line. The series of them graphed in a two-dimensional plane is a contour plot. Let's now take a look at example 6. In example 6, we want to find and graph the level curve of the function of two variables, x squared plus y squared minus 6x plus 2y, corresponding to a constant value of 15 by hand. So what would this level curve look like? This would be one of those contour lines. When it says c equal 15, what it means is that the function value is 15. So we have 15 equal to x squared plus y squared minus 6x plus 2y. Well, the next thing that we can think of to do would be, yes, you got it, complete the square on x, complete the square on y. So I'm going to leave the 15. I'm going to combine the x squared minus 6x, leave some space, put y squared plus 2y, and leave some space. In the first example for x, my a value is 1 and my b value is negative 6. b over a then becomes negative 6 over 1 or negative 6. Take half of that value and you'll get negative 3. When this factors, it will factor as x minus 3 quantity squared. This is coming from this value here. Next, we want to square half of b over a, and that gives me 9. The 9 is what I need to add and subtract into the equation so that it works out. In this case, I now have the first three terms factoring as the binomial x minus 3 quantity squared. That's where this comes from. What about for the y squared plus 2y? For the y values, my a is 1 and my b is 2. That means that b divided by a is 2 over 1 or 2. When I take half of that value, I get 1. That will be the value that will go inside the parentheses, sign included. So this is going to still have the minus 9 from here, plus y plus 1 quantity squared, where the 1 is half of b over a. The next thing we need to do is square half of b over a to find out what number we need to add and subtract to force that to happen. And the number is 1. So I add 1 and subtract 1. Oops, my 1 didn't show up. These three becomes the binomial square, and the minus 1 is still there. So now I have two binomials squared on the right, minus 9 minus 1, which is minus 10. I can add 10 to both sides of the equation to move the constant to join the 15. That would give me 25 equal to x minus 3 quantity squared plus y plus 1 quantity squared. This is a circle with a center at 3, negative 1 of radius 5. So let's go ahead and write down the ordered pair for the circle coming from the opposite of the value inside the binomials. And the radius is the square root of the constant term, in this case 5. So if I were to graph this, I would graph it in the XY plane, and I would get a circle centered at 1, 2, 3, negative 1, so centered here. 4, 5, 6, 7, 8. So this would be 5 over to this direction. 5 to this direction would put me here. Coming up 2, 3, 4, 5. So coming up 5 would put me at 3, 4, and coming down 5, 3, 4, 5, 6 would put me down here at 3, negative 6. And then do the best you can to draw a good circle. I can't draw worth beans, so mine don't always turn out too well. But this is what the level curve looks like. Let's take a look at the level curve in CalcPlot 3D and see how we did. So when we look at this one out there on CalcPlot 3D, you can see in the image right here, it's kind of faint, but it's plotted in red. And when we look at it in the 2D, you can see that it is essentially the circle that I hand drew up here. Let's take a look at that one now. Not that one, not that one. This one. There we go. I'm going to drag it down. So again, you can see this here. If you want to see it in the 2D plane, you can look at the 2D trace plane, or you can return to the menu, click on the contour plot symbol, trying to get it to show up, and then we'll click on create plot. Notice that I set the level value, the first one, to be 15, and I told it to plot one contour line. It doesn't matter how far apart they are, because I'm only going to plot one when C equals 15. And that will give me that exact level curve. Creating the plot gives me the plot that you see here. What are vertical traces? Vertical traces are to the YZ and XZ plane what level curves are to the XY plane. So in this case, we're not holding the dependent variable equal to a constant. We're holding one of the independent variables to be a constant and predicting what the trace of it would look like in that plane. So to find a vertical trace in the XZ plane, we set Y to be a constant, and then we simply graph in the XZ plane the equation we get. If we want to find a vertical trace in the YZ plane, we set the X value to be a particular constant, and then we graph the resulting equation in the YZ plane. They're called level curves in the XY plane. They're called traces in the XZ and YZ plane. Let's look at example 7. In example 7, we want to describe the equation of the vertical trace of the function below corresponding to y equal 3. Since we're setting the y value to be a constant, then this is going to graph in the XZ plane with x positive going off to the right and positive z going straight up. In this case, what we do is we're going to graph the equation. So we have z equals replacing g of xy. Our x terms remain x terms. We replace y with 3, and we graph the resulting equation. When we multiply everything out and combine our like terms, we get the equation that z equals negative x squared plus 2x plus 2, I believe. Let me check my notes and make sure that I've got the right value, though that does sound right. Yes, that is correct. So how would I plot that? Well, the same way you would plot any parabola in the XZ plane. So this is the x-axis, this is the z-axis. It crosses at 2, it opens down, and you can use x equals negative b over 2a to find the x coordinate of the vertex, which in this case would be negative 2 over negative 2, which would be 1. And the y value then, or not y value, my bad, the z value as a function of 1 would be negative 1 squared, or 1, plus 2, which would give me 3. So it looks to me like it goes through the ordered pair 1, 3, in the XZ plane. So it must look something like this. And then it's coming down like this. Hand drawing is not nearly as good as using Desmos or some other grapher, so you can see the actual picture right here. Right? Now, to see the intersection of two surfaces in CalcPlot 3D, you will have to parameterize. So we want to describe the graph of what this looks like. All right, so it's not a level curve, it's a trace. So basically what we've done is we've taken the plane y=3, which is parallel to the XZ plane, and we've sliced it through this three-dimensional surface. This graph is the trace of that within that plane. So in order to graph it and see that intersection, which is a downward opening parabola, you will have to parameterize the curve, for which we need, of course, vector valued functions. In this case, because we know that y=3, then we can parameterize our first equation with x equal to the parameter t, y=3, and then we can replace y with 3 and write our equation in terms of t instead of x, so that t is our parameter. And this, of course, gives us a vector valued function. R is a function of t, and R as a function of t is going to be t3 negative t squared plus 2t plus 2. And we graph this in CalcPlot 3D as a space curve. And you're going to get this plot that you see here. So let's come over and take a look at this in CalcPlot 3D. So what I've done when you're looking at this is I've graphed the plane right there, y=3. So you can see it's parallel to the XZ. And then I plotted my function g, which was a paraboloid. And when I look at this and I take that plane and I slice through it, it creates an intersection. That intersection is here graphed in red. And when you're looking at it, that intersection is the space curve R of t that you see right here. It might show up a little bit better from this direction in white. Let's try white and see if it shows up. Oh yeah, that's a little bit better. You can see it popping out just a little bit more there. All right. So again, in order to see the intersection of the two curves in three-dimensional space, the plane and the paraboloid, you have to parameterize and then plot the original two functions, y=3 and g of x and y, and then plot the intersection as a parameterized space curve. Let's talk now about functions of more than two variables. We've been dealing with functions of more than two variables, but all of this also applies to functions of three variables, independent, or four independent variables, or five independent variables. So let's say that we have a function of four independent variables, x, y, z, and t. So position of a point, the time that it gets there, and maybe the thing that it's mapping onto is something else related to it. I have no idea. Velocity of the object, temperature of the object, pressure of the object, something related to it. So it could be all kinds of things. Or we could have a function of three variables, x, y, and t, and then mapped to a fourth dimension. So different ways of thinking about functions of more than two variables. When we have a function of three independent variables, then we cannot draw a level curve because it's not a curve. What's coming out of the domain are ordered triples, three-dimensional shapes. So instead of a level curve in 2 dimensions, we have a level surface in 3. And this corresponds to the fourth value, the fourth variable, the dependent variable, being set equal to a constant. So a level surface is the set of all ordered triples, x, y, z, that satisfy the function equal to a constant. We want to take a look at this function here. G is a function of x, y, and z. So this is a function in 4 dimensions, 3 independent variables, 1 dependent variable. And we want to set the dependent variable value to 2 and describe what the surface looks like. So again, as you might imagine, we're going to take G and we're going to replace it with 2. And then we have it equal to x squared plus y squared plus z squared minus xy plus 4y minus 6z. And yes, you're right, you need to complete the square on all 3. So go ahead and pause the video, work it out, then turn the video back on, and we'll compare our answers. I bet you thought you wouldn't need all that college algebra again, but here you are completing the square repeatedly. So when we look at this one, over here on the left side, I went ahead and wrote down the values of half of b over a and that quantity squared for both x, y, and z. And I color coded it. So we end up with x minus 1 quantity squared with an extra minus 1 to compensate for adding 1. And for the y's, we end up with the quantity y plus 2 squared with an extra minus 4 to compensate for adding 4. For the z's, we end up with a plus quantity z minus 3 squared with an extra minus 9 to compensate for adding 9. When we move all the constants to the left side, we get 16 equal to each of the binomial squares. You may remember from chapter 2 that this is the equation of a sphere. The radius is 4, the square root of 16, and the center is at 1, -2, and 3. This level surface, when the C value is 2, represents one snapshot of what the 4-dimensional function looks like for a particular C value. In this case, maybe a W value. This is pretty much close to the end of this particular section. There is an applet inside of mathinsight.org that will let you play around with different level surfaces for a particular function. Let's look at that briefly. You'll have to scroll down towards the bottom where it starts talking about level surfaces. Here's our function 10e to the quantity power negative 9x squared minus 4y squared minus z squared. The C value that you see here in the slider bar is the value of the dependent variable. So it is a function of 3 independent variables, x, y, and z. This is the level surface when C equals 8. And I can make a level surface when C equals 9, which looks like a smaller ellipsoid sort of shape. And I could make a level surface when C equals, well, if I could get it on 6, there's what it looks like at 6. And you can rotate this and notice that it's not actually an well, I suppose it is an ellipsoid when we're looking at it. These are all level surfaces, all right? So go ahead and play around with those and see what you can learn about it from mathinsight.org. There is a video on how to use CalcPlot 3D to visualize level surfaces, which can be found on YouTube. This is the end of this particular section. In our next section, we'll take a deeper look at these functions of multiple variables, and we'll get into limits and continuity. I hope you'll join me for the next video in this series.